What's up guys, and welcome to this tutorial on question 3 of the 2016 supplementary exam. Okay, so it's called Run and Jump. It's mostly about kinematics and a bit of forces, I would say. So just to give you guys an idea, let's say kinematics and forces. Okay, yeah, so you guys know what sections this is about. Okay, so two athletes, Grant and Sue, challenge each other to a 100-meter race. Basically, the velocity time graphs for both Sue and Grant are shown. Okay, cool stuff. So we've got mass velocity time graph. We've got Sue with the dotted lines and Grant with the other line. Okay, so question 3.1.1 is a definition, which is acceleration. So define acceleration. So acceleration is the rate of change of velocity. Okay, it's also a vector. Okay, cool stuff. We get 2 marks for that definition. Okay, 3.1.2, determine the magnitude of Grant's acceleration during the first 8 seconds. Okay, so during the first 8 seconds, we want the acceleration. Okay, so the acceleration when we have a velocity time graph is equal to the gradient. So acceleration equals our gradient of the graph in a specific area. So we want for the first 8 seconds, so we want change in y over change in x. So we need to pick 2 points. I'll use this as point 1 and the origin as point 2. So what we have is change in y is going to be 8 minus 0 over change in x is also 8 minus 0. So our acceleration is equal to 1 meter per second squared. And it asks for the magnitude, so we don't care about the direction. 3.1.3 describes Grant's motion between 8 and 13 seconds. Okay, so between 8 and 13, so we're looking at this part right here. Okay, so we see that the velocity is the same. It's always 8 meters per second, so we can say that he's running at a constant velocity. Okay, so we can say running at a constant velocity. Okay, so that's his that's how I would describe it, and we get 2 marks for that. 3.1.4. Okay, so question 3.1.4 says determine how far Grant runs in 17 seconds. Okay, so we want to know how far Grant runs until this point right here, 17 seconds. Okay, so how are we going to do this? We've been given a velocity time graph, so what we care about is this area under the graph until 17 seconds. Okay, so we have to break up the areas. Okay, so the distance is equal to the areas, or the sum of the areas. Okay, I'll label these in different sections. So this I will say is 1. This will be 2. This little triangle right here, I'll say is 3. And this area over here, I will say is 4. So the sum of the areas. So the distance is equal to the sum of the areas, which is equal to area 1 plus area 2 plus area 3 plus area 4. Okay, and that is equal to, so if we look at the first part of this graph, we can say that area 1 is a triangle, so it's equal to a half times the base, which is 8, times the height, which is also 8, plus area 2 is a rectangle. Let's actually clean this up. Okay, so we have 1, 2, 3, 4. Area 2 is a rectangle between 13 and 8 seconds, so I'm going to go 13 minus 8 times the height of the rectangle, which is also 8, plus area 4, or area 3 rather. Okay, so area 3 is a triangle once again, so I'm going to say plus a half times the base, which is 17 minus 13, times the height, which is going to be 8 minus 6, plus the last rectangle, which is also 17 minus 13, times the height of 6, I think, yeah, of 6. Okay, and if we plug that into our calculator, we get that the distance is equal to 100 meters. Okay, cool stuff. Oh, the hardy dolls are making some noise. Okay, so question 3.1.5. The two graphs intersect at point X. Yes, they do. What can you conclude about the athletes at this point? Okay, so for Grant at point X, he's running at a velocity of 8 meters per second, and for Sue at point X, she's running at a velocity of 8 meters per second. So we can say that they both have the same velocity at this point. Okay, and we get 2 marks for that. And then it says, determine how long Sue takes to complete the 100 meters. Okay, so how are we going to do this? Okay, so we want the area for Sue. So we're concerned about the area for Sue. Okay, so Sue's graph is this graph I'm going to draw in blue. This graph right here. Okay, so we want to determine the time she takes for the 100 meters. So 3.1.6, I'm going to say that the distance is equal to the sum of the areas, okay, which is equal to area 1 plus area 2. Okay, so the triangle, this triangle is 1, and the rest is going to be 2. The rest is a rectangle. So we know the total distance we wanted to run is 100 meters, is equal to area 1 is a half times the base, which is 15, times the height, which is 10, okay, plus area 2, okay, I'm going to say is the height, which is 10, times, okay, so it's somewhere along this line is where she reaches 100 meters. I'm going to say that's point T. Okay, so I'm going to say the base is T minus 15. Okay, so that would give us the area. If we look at this equation, the only unknown is the value T. So if we put that into our calculator, we get that T is equal to 17.5 seconds. Okay, so she actually loses the race. So she would reach 100 meters somewhere here. Okay, and that's the end of that question. So we move on to 3.2. Okay, so the springbok is the national animal of South Africa. It gets its name from its ability to jump high, basically. Cool stuff. When a springbok is startled, it crouches down and then pushes on the ground, accelerating vertically up at 35 meters per second squared. So what is this? This is an acceleration. Okay, for a distance of 0.7 meters. So that's a distance. Okay, when it straightens its legs. When the legs are fully straightened, the springbok leaves the ground and rises into the air. Okay, so question 3.2.1 says identify the action-reaction pair of forces involved in the process of the springbok jumping. Okay, so obviously when the springbok jumps, the springbok exerts a force on the ground. So one of the forces is the force that the springbok exerts on the ground. Okay, so the other force, remember, we just need to change the positions of the two forces. We can say the reaction is the force that the ground exerts on the springbok. Okay, and that is our action-reaction pair. And we get 2 marks for that. Question 3.2.2, explain why the springbok accelerates upwards even though the forces in 3.2.1 are equal. Use one of Newton's laws to help you in your explanation. Okay, so basically this is an explanation question. I know you guys hate my handwriting, so I'm just going to say the answer out to you guys. Okay, so I will say the action-reaction pairs act on different objects. Okay, so force on the ground, the force that the ground exerts on the springbok is greater than the weight of the springbok, resulting in an upwards resultant force. So the resultant force on the springbok is upwards because the force that the ground exerts on the springbok is greater than the weight. Okay, so by Newton's second law, the resultant force produces an acceleration upwards. So that would be the complete answer. So the use of 1 Newton's law is Newton's second law to explain that if the force upwards is greater than the force of weight, then the springbok will move upwards because F net is equal to ma. Okay, so there's an acceleration because there's an upward net force. Okay, so I hope you guys understood that. I hope that makes sense for you guys. Okay, then moving on to question 3.2.3. Okay, 3.2.3. Treat the springbok as a single particle for the following question. At what speed does the springbok leave the ground? Okay, so how are we going to do this? We can see that there is a constant for when it bends its legs and releases, there's a constant acceleration. So we can use UVATs. UVA. My U and my V can look very similar. ATS. Okay, so we know the initial is 0. The final is what we're looking for, so it is the unknown. The acceleration was being given as 35 meters per second squared, and we're going to take upwards as positive. The time is also unknown, and S is the distance, which is 0.7, which is unknown. Okay, so we can use the equation, let's see, V squared equals U squared plus 2AS. V squared is the unknown, equals U squared, which is 0, squared plus 2 times acceleration times the displacement. Okay, and square rooting both sides, this basically goes away, so we can square root both sides, and V is the only unknown here, so we can say that V is equal to 7 meters per second. Okay, and it asks for the speed, so speed is a scalar, we don't care about the direction. How high above the ground does the springbok jump? Okay, 3.2.4. Okay, so this time we're looking at an object or the springbok in free fall. Okay, so this is after his initial acceleration. He's now in free fall, or the springbok is now in free fall, so gravity is acting on him. And once again, we can use UVATs, UVATS. Okay, so the initial is going to be the final from before, so let's take upwards as being positive once again. So we have 7 meters per second. At its maximum height, okay, at its maximum height, the velocity equals 0, so V equals 0. The acceleration is minus 9,8. Okay, the minus because we've taken upwards as possible. The time is unknown, and the displacement is unknown. And we're looking for the displacement. So again, we can use the equation V squared equals U squared plus 2AS. V squared is 0 squared equals U squared 7 squared plus 2, acceleration minus 9,8 times S. The only equation, the only variable that's unknown is S, so we can solve for S. S is equal to 2,5 meters. We can even say above the ground for a more precise answer. And we get 3 marks for that. And that question was worth 29 marks. So not too bad of a question. 29 marks is a lot. I mean, yeah, so that's quite nice. And we got through in about, I'd say, 17 minutes, probably less than that. So yeah, good stuff. Thanks for watching, guys, and I hope you found it useful. Let's see, next video we've done question 4, so we'll go on to question 5. Okay, thanks for watching, guys. Cheers.